this is a lecture which is going to pick up where we left off from lecture 18. In lecture 18 we covered electric potential energy, we remembered electric field, we introduced electric potential as being the electric potential energy per unit charge. We defined electric potential as the electric field times the distance from the negative plate, and we found the electric potential at some distance r from a point charge q to be kq over r. So we'll start with an example in this lecture. This example is similar to one we did in chapter 29, lecture 9 specifically. In that lecture we had two charges along the x-axis, a positive and a negative. Our negative charge was 5 millimeters to the right of our positive charge, and in lecture 9 we asked the question, where on the x-axis was the electric field equal 0? We won't go through all that work here again, but just as a quick reminder, for the net electric field to be 0, the sum of the electric field is the electric field due to charge 1, let's say that's the positive, plus the electric field due to charge 2, we'll call that one charge 2, that had to be 0, so the fields had to be equal and opposite. We thought about each of our three possible regions. In between the two charges, the electric field at some point here, due to the positive charge, would be to the right. Due to the negative charge, would be to the right. So the electric fields here would not be in the opposite direction. So that's why the electric field net is not 0 in between the two. Over here to the right of charge 2, our electric field due to charge 1 points to the right, but we're very far away from a small charge. That would give us a small field. Our electric field right here due to charge 2 will point to the left, so the two fields are in the opposite direction. But at this place, we're very close to a big charge. That would make a big electric field. The two fields couldn't be equal here. That left out here. So out here at this point, our electric field due to charge 1 points away. We're a small distance from a small charge. That gives us a medium field. So there is our E1. Our electric field due to charge 2 points in towards charge 2. We're a big distance from a big charge. That gives us a medium-sized field. We set these two to be equal. So we said E1 equals E2. When we did that work, we found that the distance between the two charges, that distance x, was 12.1 millimeters. Okay, so that's a recap of what we did in chapter 21, lecture 9, to find the net electric field to be 0. Now let's do an potential question. Where is the net electric potential equal to 0? Okay, so now this question is going to be different because electric field and electric potential are different. Electric fields are vectors. We had to carefully consider the direction. Okay, we had to draw the arrows for the electric field to get our answer. But electric potential, that symbol is V, that's a scalar. We can't draw any arrows here. Because they're scalars, they only have a magnitude. So for our electric potential to be equal to 0, we want that the sum of the potentials, V1 plus V2, we want those sums to be 0. To get these two things added up to be equal to 0, what we have to have, V1 and V2, we'll say must have opposite signs and equal magnitudes. Okay, MAG for magnitudes. So opposite signs, that's not going to be too difficult. We know V is KQ over R. This charge is positive, that's going to be a positive potential. This charge is negative, that's going to be a negative potential. So we need to find the place or places where the potentials will have equal magnitudes. So let's think about where we can find. So let's see. So due to Q1 equals plus Q, V1 equals K Q1 over R1. That's positive everywhere. And the electric potential due to charge Q2, which is negative 2Q, V2 is K times Q2 over R2, will be negative everywhere because that charge is negative. So Q1 is a small charge, Q2 is a big charge, Q1 equals Q2 equals. If we want the potentials to have equal magnitude, we're going to need to be closer to the small charge. That's how we're going to get equal magnitudes for our potentials. Okay, so what we have to do, so for equal magnitudes, must be closer to Q1. If you didn't see that by looking at the problem, that's fine. You would see that work out when you did the math. So where can we find places that are closer to Q1 than to Q2? Well, I can think of two places. So one spot where we could be closer to Q1 than Q2 would be out here somewhere. I'm going to call that spot P1. And another place where we could be closer to Q1 than Q2 might be over here, P2. So I can think of two possible places. Let's work through that math and see what we get. Okay, so I think maybe I'll just start with a fresh diagram and a fresh sheet of paper. So let's start for our first point. So I've got my charge 1 here, charge 2 here, my point 1 is here. I know that I have to have opposite signs, equal magnitudes. So I'm going to say V1, so my net potential V is V1 plus V2 equals 0. So I'm finding where the net potential is 0. V1 is K times Q1 over R1. V2 is K times Q2 over R2. That has to be 0. What can I put in next? Well, I've written R1 and R2 in my equation. I should specify R1 and R2 in my picture. R1 is my distance between charge 1 and point 1. R2 is my distance between charge 2 and my point. There's R2. I know my distance between my two charges is 5 millimeters. So if I look at this geometry, I might recognize that R2 is R1 plus 5 millimeters. So this distance is this plus this. I also know that Q1 is plus Q and Q2 is minus 2Q. Okay, I'm going to put those things in. K times Q divided by R1 plus K times minus 2Q divided by R1 plus 5 millimeters equals 0. This is looking kind of nice. I'm going to take this term over to this side. So K times Q over R1 equals K times 2Q over R1 plus 5 millimeters. I've got K on both sides of the equation. They can cancel. Q on both sides. They can cancel. Now I'm going to do some cross multiplying. R1 plus 5 millimeters equals 2 times R1. So 5 millimeters equals R1. That means 5 millimeters to the left of charge Q1, we will have a net potential equal to 0. Okay, so that's my first spot. What about my second spot? So the net potential equals 0 at 5 millimeters left of Q1. Okay, that bit's done. All right, what about my second place, P2? I'll just start with a new diagram again. Here's charge 1, here's charge 2, here's my point P2, and I know that my distance between those two charges is 5 millimeters. My net potential is V1 plus V2 equals 0. K times Q1 over R1 plus K times Q2 over R2 equals 0. R1 is between my point and my charge 1. R2 is between my point and my charge 2. Here I might notice that R1 plus R2 equals 5 millimeters. That means R1 is 5 millimeters minus R1. So R2 is 5 millimeters minus R1. Let's put this information in. So K times Q1, that's plus Q, over R1, plus K times Q2, that's minus 2Q, divided by R2. R2 is 5 minus R1. That has to equal 0. I'll take this term to the other side. I've got K on both sides. Divide through by K, divide through by Q. Now I'll do some cross multiplying. 5 millimeters minus R1 equals 2 times R1. 5 millimeters equals 3R1. R1 is 5 millimeters divided by 3, 1.67 millimeters. So our net electric potential is equal to 0 at 1.67 millimeters right of Q1.